right, this is chemistry lesson 6.05 over double and triple bonds and how that affects hybridization. So we're going to start off actually from a different standpoint. We're going to look at the couple of structures that we've already done. And let me grab my markers here. Should have done that ahead of time. So let's start off with that carbon tetrafluoride we had on the previous page. We have a carbon. Let's keep down. My ducks in a row here, guys. All right, stay on page here. We've got our carbon and our fluorides. And I've got my bonds. And in the last video, we said that if we look at the orbital diagram notation for carbon, we only have 2 unpaired electrons, so it should only be able to form 2 bonds. But in fact, we have 4 bonds around here. And what it does is it elevates the S and it drops the P's, and we get these 4 sp3. And then we have 1 electron in each of these orbitals that combine, and that's how we're able to form the 4 bonds. So to determine hybridization, you have to do 2 things. The first thing is you have to count the number of what are called sigma bonds. Sigma bonds. And the unit for sigma looks like a referee's whistle a little bit. So what we have up here, by the way, one of the things we didn't mention was when these guys hybridize, we knew that S is a sphere and P looks like an infinity sign. So up here, and I have mine drawn in, I have a color copy. So here I have an orbital, an orbital, and an orbital. And what I'm looking at here is sp2. So what has happened is that 2 of the p orbitals and 1 of the s orbitals have elevated. The s orbital has elevated and 2 of the p orbitals have dropped down. And this is the new shape. Instead of having a sphere infinity infinity, these are the 3 sp2s. Over here, I also have sp2. So these 2 molecules both have sp2. And this area here where we have bond overlap, that's what this says, bond formed by sp2, sp2 overlap, is called a sigma bond. A sigma bond is a bond that's formed by hybrid orbital overlap, or formed by direct orbital overlap. Well, you guys know there's not 2 p orbitals, there's 3. So what happened to the 3rd p orbital? Well, it's still there. And for this molecule, so let's say it's the PZ. So we have the PZ is still up here. So this is the PZ for this molecule. And here I have the PZ for this molecule. So it's kind of just, and it sticks up from the molecule, the plane of the molecule. So what we see is that these 2 carbons, the bond between them and these hydrogen, this is a flat plane. So we get this planar molecule. And these p orbitals stick up, and they're kind of big enough that they overlap. So we get overlap between these p orbitals, and that's called a pi bond. Well, because this is a direct overlap and this is an indirect overlap, this sigma bond is much stronger. So the sigma bond is formed by direct orbital overlap, and it is much stronger. The pi bond is formed by an indirect overlap of p orbitals. Indirect overlap of p orbitals. and it's weaker than a sigma bond. So if I look at, let's look at a couple of structures here. If I have cyanide, which we've already drawn, I have one sigma bond. So this guy's sigma. And I have two pi bonds. Not just, so I have actually two sets of p orbitals overlapping. So this is a pi bond, and that's a pi bond. So let's do a little bit of practice. Let's do both the Lewis structure and look at the hybridization for carbon dioxide. So this would be example 1. Here I've got, these are all single bonds. They're all going to be sigma bonds. So here I have 4 sigma bonds. So let's finish this first example. So the number of orbitals that I hybridize has to add up to 4. Well, I can do a max of an S, a P, a P, and a P. So this hybridization is going to be sp3. All right, let's do example 2. All right, let's do carbon and 2 oxygen, and we're going to do both the Lewis structure and hybridization. So oxygen has 6 electrons and carbon has 4. So we've got 4 valence electrons and oxygen has 6, so I need a total of 10. I don't have to worry about my skeleton structure here, so I've got 2, 4, 6, 8, 10. Now I need to do my octet check. Oxygen has an octet, 2, 4, 6, 8, but carbon does not. So 2 of these pairs have to be lassoed and brought down into a double bond and then a triple bond. So I end up with 3 bonding pairs in between carbon and oxygen. And when I redraw it with dashes, my molecule looks like this. Whoops, is that right? Yeah. Okay, so what I need to do now is I need to determine how many sigma bonds I have. And that is 1. So only this center bond is a sigma bond. This is a pi bond. And this is a pi bond. So I have 1 sigma bond. And I also have to count lone pairs. Here, I have a lone pair. So I have 1 sigma bond. Let's talk about carbon, just carbon. And I have 1 lone pair. So this is an orbital and this is an orbital. Well, if I have to have a total of 2 orbitals, that means I'm going to have a combination. It's always at least 1 s, and I'm going to have 1 p. So I call this hybridization sp. So this molecule has sp3 hybridization. This molecule has sp hybridization. And let's do one more. Or let's do a couple more. So let's do example 3. I'm going to put him up here. Let's do water. Hopefully you know the formula for water is H2O. So I've got 2 hydrogen and 1 oxygen. Hydrogen each has 1 electron. So I'm going to have a total of 2 valence electrons here. Oxygen has 6, so I need a total of 8 valence electrons. When I draw my stick structure, I'm going to put, let's go to green. I'm going to put oxygen in the middle and hydrogen on either side. And we're going to see later this isn't quite the right shape, but here I go. I've got 2, 4, 6, 8. And when I redraw this with bonding, I have H-O-H with lone pairs. Okay, so when I count my sigma bonds, I have 2. When I count my lone pairs, I have 2, for a total of 4 So I have 2 sigma bonds plus 2 lone pairs, so I have 4 orbitals. Well, where am I going to get 4 orbitals? I'm going to have to combine an S, a P, and a P, and this is going to be sp3 hybridization. Okay, example 4, let's do one more. And this will also give us some practice drawing Lewis structures. Let's go with, do I want to do, let's do a 2 carbon and 4 hydrogen. So pause the video and see if you can do this problem on your own, and then I'll walk you through it. Okay, welcome back. So let's look at the solution for this. I'm going to do this guy in pink. Each carbon, so I've got 2 carbon, and these each have 4 valence electrons. So for my carbon, I have 8 valence electrons. My hydrogen each have 1, so I've got 4 hydrogen valence electrons for a total of 12 valence electrons in this structure. Now, in this case, I'm going to put my carbon together in the middle, and I'm not quite sure where my hydrogen are going to go. I'm just going to kind of arrange those around the outside symmetrically. Now, I know my hydrogen only need 2 electrons, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8. You know what? I don't like the way. I was kind of putting my carbon on the corners, so this will work. All right, so this hydrogen has 2, this hydrogen has 2, this guy has 2, that has 2. Remember, hydrogen only needs 2. This carbon has 2, 4, 6, 8. So this carbon's good, but this carbon only has 2, 4, 6. So that means that we have to get out our electron lasso, and this carbon is going to bring down. So this is actually the bonding pair. That's why drawing it on the diagonal wasn't a good idea. But this is my bonding pair, and I'm going to have to drag down a second pair. So when I do that, so now I've got every hydrogen, I've got 12 electrons, 2, 4, 6, 8, 10, 12. Every hydrogen has 2. This carbon has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. So when I redraw the structure, it's going to look like this. Whoops. Okay, so what's my hybridization? Well, this is a sigma bond because it's a single bond, so that's a sigma. That's a sigma, and we're looking at the hybridization around this carbon. This is going to be a sigma, but the second one is going to be a pi bond. So that means that I have 3 hybridized orbitals around carbon, and that's going to have to be an S, a P, and a P. So the hybridization here is going to be sp2. Did you get that? All right, what you're going to do now is you're going to go back through all of the Lewis structures that you've already created, and you're going to find the hybridization on all of the atoms by counting the number of sigma bonds and the number of lone pairs. All right, so off you go with that. Thanks for watching and have a great day.